Okay, so we continue. So, well, the next topic we will learn is the so-called refraction. What is refraction? Well, the definition of refraction is that there is a change in direction of energy transferred when a wave travels from one region or from one medium to another. So, well, and this happened because this is due to change in wave speed. So maybe I put it here. So it's a change in direction of energy transfer due to change in wave speed. And wave speed depends on medium, so therefore it can only happen when a wave travels from one medium to another. So therefore, what happens is the change in direction of the energy transferred. And the reason why this happens is because there is a change in the wave speed. And when does it occur? It occurs when the wave enters a new medium. So the classic example will be you just use a laser beam and then you send this beam of light from glass into from air into glass. For example, this is a piece of glass and this is the air, or you can say the vacuum. And then we study a light ray, and the light ray coming in, hitting the boundary between the two media, and this we call it the incident ray. Then as it hit the glass, it will not continue to travel in a straight line. Instead, it will bend a little bit. And this is what we call refraction. So this ray is called the refracted ray. Well, similarly, you may not need to use light wave to study refractions. You can also study refraction using water wave. And let's say I have two regions. One region is a deep water region, and another region is the shallow water region. You can imagine that this is close to the beach, so this is a region with shallow water, while this is closer to the ocean, that the water is deeper. And then I can still have the ray traveling, representing the direction of the energy transferred through the of the water wave, and then it will also will bend this way. So it will also involve a change in the direction of energy transferred. Well, however, as we emphasized it before, the interesting part of the water wave is that its wavelength is relatively large and can be observed using a water tank, or just regularly in daylight we can observe it. So therefore, when we really sketched the wave, what's it called? Wave fronts. So we can draw the wave fronts on the incident part, so the incident wave fronts. The reason why I can draw this is all because I know the incident wave fronts are perpendicular to the ray. This is one properties we emphasized before, and they should be equally spaced because the wave is in the same region. If you remember about the logic behind is we have the same V because we are in the same region, so therefore we should have the same, and we have the same frequency since we can never change the frequency, and then we have the same wavelength, lambda. Therefore we should have a uniform spacing. I try my best to sketch it uniform. I think this may be a little bit shifted here, like this. Now then how about the wavefronts on the other side? Well, naively, of course, you can still draw the wavefronts following what we learned, just to ensure that the wavefronts are perpendicular to the ray. Well, however, we need to know that these wavefronts comes from these wavefronts. So therefore, instead of randomly start drawing the wavefronts, we should start drawing the wavefronts at the point where you have the wavefronts on the boundary. So therefore we draw a line, and this line cannot be this because it has to be perpendicular to the ray. So I'm going to draw something like this. So similarly, this one has a parallel to the first one, like this. This is correct in the sense that they are now perpendicular to the ray, the only requirements we need. So therefore, you see, automatically, the ray front in the second region will be closer to each other, having a shorter wavelength. So here, we have a shorter wavelength. And the important thing is we deduce it just based on two principles. First, that the wavefronts are perpendicular to the ray. And the second one is we need the wavefronts on both sides of the media to match at the boundary. So we need continuous wave fronts. So we need this location here, and then need this one. So well, therefore you found out that when there is a change in the wave speed, in fact there should also be a change in wavelength. This is something that we will come back to later. But never mind, the bottom line is refraction is a name we use to describe the phenomenon when the ray changes its direction of energy transfer when it travels from one medium to another. And the reason why there is a change in the direction of energy transfer is that since the wave enters a new medium, that its wave speed will change. And because its wave speed changes, therefore the energy directions is changed. Now we have to understand why. Why change in wave speed leads to change in direction. It turns out that we can have a metaphor that we can understand it. But this metaphor is the following. It's that let's say I have two regions. The upper region here is the region where I can travel faster, that the wave speed is higher. So this is a region where speed is higher. And then the lower region is the speed, is a region where the speed is lower. And then let me color the second region. Like this. And then now, as we emphasized before, there is a ray coming in. Now, I want you to imagine that this ray is actually the motion of a car, and this, as normal cars, it has 4 wheels. Like this. Now, then this car will continue to move forward until it hit this point. Now, what's so special here is that I want you to focus on the location of the 4 wheels. At the very beginning, you have the 4 wheels located in the same region of space. 1, 2, 3, 4. So just imagine like the cars that the 4 wheels, and then we have to, let's clarify first, that the driver on this car does not turn the wheels at all. So all he does is to turn on the engine. So the car is moving forward. And then now, since these 4 wheels are in the same region, then these 4 wheels will travel at the same speed. So therefore, it will just move forward. Well, however, as this car meets the boundary, we'll have these 3 wheels that in a region that it can go at a higher speed. However, for the wheel here, this wheel will enter the region that the speed is lower. So therefore, at the end, what happened here is that the wheel in blue will travel a smaller distance as compared to the wheel in yellow. And then we can just identify that because the location of the front wheels basically tells me which direction the car is heading to. Therefore, it's now no longer heading in the same way. It will now head this way because this wheel has displaced more than the wheel in blue. So therefore, as a result, this will bend this way. So this explanation or this story can explain why change in wave speed can lead to change in direction. Okay, I will specify here. This one, it moves faster. Or this one, it moves slower. Like this. Okay. So this is just a understanding. This sometimes will help you to solve some problems. But of course, it's very hard to really test you this metaphor in the DSE examination. But never mind, this turns out to be quite constructive to know. Well, at least I found it interesting. Yeah. And also, this metaphor is not naive. It's not just a funny story I make it up. Sometimes I make up funny story, but not this one. This one is actually a very classic. It's so classic that even you study physics in university, the professor or the textbook may also use this metaphor because it's really so interesting. And the reason why we can only use metaphor but not a really explanation is because refraction is actually a quite complicated not a complicated phenomenon, but the explanation is complicated. It will involve a lot of mathematics. Also, you need to know much more advanced theory before you can really not understand, but explain it. So this is the best we can do. Okay, now then we have introduced the term. Now I hope you are convinced that the change in wave speed can lead to change in energy transfer. And using rays, the representation is simple. You just see the ray kind of broken when it enters or when it crosses the boundary. But using wavefronts a little bit more sophisticated. But the rule in mind is just to put the wavefronts perpendicular to the ray. Okay, now then the next part is, well, as I said, we are not going to explain it, so let's describe it. Well, Snell's basically what he did is just he make a lot of observation on refraction, and then he finally concluded a law that can summarize refractions. Well, so as a law, it's also just a collection of observations. So what is this law? This law is written this way. Well, for this one, it is quite complicated. Well, first of all, this diagram, this equation should always be accompanied with a diagram. So I have a diagram with the two medium. So medium 1, I will use a number to describe the medium 1. We call it N1, and then another medium N2. Give me a second.